everyone. I love that previous presentation because it pointed out such an important thing, which is effective uncertainty, right? There's certainly one model, but this incredibly great, complicated ground motion model gives you very different results based on the input to that complicated model. And that means that if we're looking at a bridge, or what we'll look at here in networks, boy, if you don't take that into account, you get completely different answers. And so what we're trying to do is a little simple-minded. We say, well, this is great. Here are these complicated models, complicated ground motions, all these bridges, they all have different properties, imperfect information, poorly understood behavior sometimes. What is it we really should include in our models? What do we need to include in our models? And so the title is Identification of Critical Ground Motion Bridge Features for Performance Assessment of Regional Transportation Networks. So it's a big thing, and we're actually just getting started. We were selected for funding last year, but it started this week. And we love being able to see these presentations because there's a bunch of places we want to hook in and work with you. And I know Greg Dearline is talking this afternoon as well. So I think that's one of the great things about Peer is if we can get together and kind of exchange information and concepts, we're all going to be much better off. So there are a bunch of people who are helping do this work. The original ground motions we'll look at were developed with funding from NSF and USGS. A lot of the bridge stuff we've done was funded by DOT, by Washington State, from PacTrans Regional Center. And then we've been using TAC, which is Texas Advanced Computing Center for Multisource Simulations. And then now the work we're doing is funded in part by Peer, and we hope to be using a lot of Sim Center tools. And then now the Cascadia COPES Hub. And they're looking really at regional behavior. And so one of the things I did is when I heard the talk about gas pipelines, my ears pricked up because all of a sudden someone said, well, can we do natural gas too? And of course, that wasn't part of our plan. And my question for you is going to be, well, how little information do I need to just make it through the process? So I'd like to talk to you after this meeting. This is a very exciting outcome. Okay, so what we're trying to do is to look at different sources of uncertainty and just see how much they affect the performance of a seismic network. And of course, we look at simple networks because of the time involved. And then once you have that understanding, the idea is if you're doing a performance evaluation of a network, what is it you really have to include into your analysis? It's always going to be a trade-off, right? So you need, what are the contributions to uncertainty? You also care about how much time it is to go out and collect that information. So if you need to know, for example, the site conditions at every single bridge in your network, and you're going to go out there, you're going to have to do new boreholes for every single bridge. Well, maybe that's not going to happen. So what you include in your analysis is a trade-off between getting the best answer you can, but also the cost of getting some of the information that you might need. Okay, and the other tool on the side is we're going to try to use the Sim Center tools for most of the things we're doing. And so we want to coordinate with them, and that's a big part of our work, is to work with them and give them some feedback on the use of the various tools. Okay, so essentially it's a huge parametric study. And we're going to be looking at different kinds of earthquakes, both the M9 Cascadia subduction zone earthquake off the coast of the Olympic Peninsula, and then a Seattle earthquake, which is going right through downtown crustal fault. We're going to be looking at two networks. One of them is Puget Sound region, which is essentially I-5, 990, and a couple other highways, but also the Olympic Peninsula. And the focus on Olympic Peninsula is in part because the COPES hub is supposed to be looking at the resiliency of the Olympic Peninsula for earthquakes, tsunamis, and a bunch of other things along the way. So what are the things we want to look at? Well, certainly we want to look at the earthquake scenarios. That's the previous talk looked at, which is, in our case, we have 30 different sets of motions. Our model is a lot simpler. We're not getting down to 2 meters or anywhere near there on that. But we do have 30, which is good. Site conditions, sometimes we know them well, sometimes we don't. Of course, all the properties of the bridges, because we're talking about a lot of bridges, we're not going to do a detailed finite element model of every single one of them. And then also, what is a methodology you're using to assess the network? So the fragility curves that are available out there There's some of them are just kind of generic bridges based on age, or you go into detail and you start saying, well, I have 20 categories of bridges, and I'm going to try to develop them for every single type and then apply them in a very detailed way. There's a single degree of freedom methodology we've developed, or you go through and just develop tons of models and just run them. Okay, so that's kind of the plan. And what I want to go through is essentially the building blocks, because of course, we're not going to do all this, develop all that based in just 1 year. The motions have been done already by USGS and with funding from National Science Foundation, 30 rupture scenarios, different extensive faults, all for magnitude 9 earthquake. As part of the current project, it's going to be redone with FEM, excuse me, at a higher resolution. These were going down to about 1 second, which gets to the problem that you're talking about, because most bridges don't have periods of 1 second. They're way below that. It's going to be redone, and also going to be done for Seattle Fault and the South Whidbey Island Fault, which is just north of town. So we're going to get a new set of motions. The grid right now is 1 kilometer per point. We have in some places very detailed site conditions, maps like this, but also arrays of borings. As you imagine, if you're in the city, they're everywhere. The further you get away from the city, the harder you have getting actual borings or site conditions. We developed bins of ground motions based on work by Audi et al. And essentially, we have 4 different site conditions, and each of them, we do essentially 10 calculations for each site. Sometimes we do 30. And the idea is we can try to get the idea of what a local site condition will do to a ground motion, but we do it in a probabilistic sense, and since we run it through different kinds of arrays, even for the same V sub S 30. We have a detailed database, which has 582 bridges. It's going to have about 700 by the time we're done. And by detail, we mean size of the shortest column, amount of reinforcement, not every single dimension, but the ones you might care about the most, shear keys, what kind of abutment it has, and stuff like that, more than what would typically be a fragility curve. And you can see what's common for the United States is on the left-hand side, you have all the dots, which are the pre-1975 bridges. And on the right, you have the newer ones. And because the construction of the interstate system, most bridges, of course, are old. And that contributes to the uncertainty of what's actually being built. Just as one little example, we have dozens of bar charts like this. This is actually looking at a subset of bridges. We have shear keys. If you're worried about a bridge moving transversely, it turns out that shear key is super important. And it just shows that depending on the kind of bridge you have, you're likely to have one shear key or another. This result is one you would expect, which is if you have a box bridge, you have external shear key. The other bridges have different kinds of shear keys. So this plot isn't important in itself, but it's really a representative of maybe, I don't know, 30 or 40 kind of variables we kept track of in terms of location, in terms of year construction, to try to figure out what the inventory looks like. Now, once you have characterized sets of bridges based on typical properties, we have an OpenSeas model here. And again, we ran, I think, something like 40,000 simulations, different locations, different soil conditions, different realizations, different profiles, different structural properties, different assumptions that are being made to get this huge bin of outcomes of simulations. I shouldn't use the word huge when I'm around David, because we got to gigs and we thought that was pretty impressive. And so for every single bridge, of course, you have the response of the bridge. We have most of the details stored, not all because of size. But they are detailed models, and this plot has way more detail than you need, but it has shear keys and bearing pads. Things are bouncing into end walls and doing all the standard stuff you'd expect for a nonlinear bridge. Once you get the deformation of the model, we're using some fragility curves we developed for column spalling, for bar buckling, for failure of the shear key, things like that. And the idea is that for every single combination of realization, ground motion profile or site type class, profile, location, bridge type, element, you can get a likelihood of failure of that particular element. And so in this case, the likelihood of concrete falling on the left for a column and likelihood of bar buckling on the right-hand side. So I'm not kind of ran through things as essentially examples. We could imagine the kind of thing you get when you're all done in terms of just talking about what is a likelihood of something happening for a given type of bridge. Way too many bars up there, but let me just explain what the result is to characterize it. So there's two locations because the ground motions for an M9 earthquake will be very different if you're on ocean. So ocean shores is at the shore. Port Angeles is on the Olympic Peninsula, but kind of on the other side of it. On the top, you have likelihood of falling, bottom, you have likelihood of falling. But then as you go from left to right, there's 4 different soil profiles that we have bins for. And for every single soil profile, there's 30 realizations of earthquakes and 10 soil profiles. So every single bar there represents 300 outcomes for a bridge. And then the various kinds of bars are just different properties of the bridges. In this case, we're varying 2 things. One of them is, does it have a shear key that's working? And 2, what's the height of the column? And the shear key tends to pin things at the ends. Height of the column, of course, changes the period. And the details aren't so important. But if you look at the results down here, you'll see that if you take the shear key away, make the column really high, and put in Seattle or in Port Angeles, where there's a sedimentary basin, you start exciting these bridges, which are long period, sitting on a long period site during an earthquake. So the kind of results you get out here are the ones you expect, but now there's actually numbers, which is if you're in Port Angeles and you have a certain kind of bridge, here's a likelihood of spalling. Now, we've done this for a bunch of different cities, a bunch of different models. The next step, of course, is develop fragility curves, because the runs are there. We still have to decide the model of the curves and exactly how we're going to categorize them. Okay, so we haven't started yet. The funding came in a week ago in terms of what we're doing for here. The first thing we need to do is kind of settle on what intensity measures we want to use. It's a bit complicated because a lot of these bridges have very nonlinear responses. In other words, when that bridge moves, it hits that shear key right off the bat. So the initial period is probably not what we care about. And then we have to categorize, we have, I think, something like 100 different bridges. Are we going to develop fragility curves for each of those and apply them, or we're going to group them and all that kind of stuff. And the idea is to do the most complex version, which is you do all the 30 simulations and the ground motions and the bridge model and the soil type and all these kinds of things. And at what point can you cut back and say, well, I don't really want to do this every time I want to look at a network, because everything I've shown you so far is sort of individual bridge. But if you look at a network really gets subjected to a realization, not a bunch of them all together, right? So you have to really look at the network performance for each realization, and then look at that network performance, and then do statistics on that afterwards. So we're hoping that the NESIM tools actually are going to be helpful in organizing that and trying to do the parametric study. So we want to work with them for sure. We have the benefit of starting a year later than 3 other NES regional network. So we really want to meet soon and see to what extent can we learn from each other and what extent can we help each other. There's so much work to do that the more we work together, the better. And then the other thing is the Cascadia Coast Hub has a very, very strong social impact component to it. So we're now working with a lot of sociologists and different people who I am enjoying learning from, talking about questions like, if you have an earthquake, how does that impact various communities? And one of the fun things about Olympic Peninsula is you have itinerant workers, you have vacationers, you have people who live there, you have Native American tribes, you have all kinds of different governments. And part of what we're going to look at is to what extent do earthquakes affect communities differently. That's fun. We've never done that before, but I'm working with some people who I think are interested in. So that's the overall plan, but then you still need a detailed plan, that's great. But what exactly are the networks you can look at? What exactly are the motions you're going to run and how many runs and stuff like that to do that work. And that's what we're planning on doing soon. And we're looking forward to doing this project over the next year or so. Thank you.
Thank you very much, Marc. And I would like to thank you especially for agreeing to give this talk while your project just started. So, but I think this is a perfect example of your opening remarks that this is the purpose of this research forum. So I think your position, your project is in the perfect position to interact with others and see what they are doing and maybe find points of intersection that will redefine your plan. So thank you for agreeing to give your presentation in that early stage.
We are enthusiastic about that opportunity, absolutely.
Yeah, so we are about 9 minutes behind the schedule. If we are done with all the presentation, but if people are willing to go on a break for another 6 minutes, we can entertain few questions to David, Jenny, Floriana, and Marc. Any questions from the floor or online? And then you have a 15-minute break.
Good questions and
Do you guys want to come back up? Or is it okay?
my question is for you.
Sorry. Yeah.
Great preparation for this project that you've been doing. My question is, when I think about network, I think about functional.
Yep. Yep.
Emergency response. Are you going to take the next week and then the bridge damage quantified and fragility estimated to impact on?
Right. We're going to try. So the hard thing is what you're trying to estimate is actually not even the capacity of the bridge or what you're really trying to estimate is the decision that the bridge owner is going to make after an earthquake. And so what we're going to do is we're going to speak to mainly Oregon and Washington Department of Transportation, but some local people and show them some pictures and say, what would you do with a bridge like this? So it's really more kind of psychology than anything else, because for reinforced concrete bridge, the axial loads are so low. Some of these columns are in terrible shape, but if it's not a shear failure, you could probably still drive a truck, but they'll never do that. And so for functionality, we're interpreting that as the functionality based on the decision-making that an agency is likely to make.
So you're going to include that in the
Yes. It's just going to be at the end, another fragility curve, essentially, right? Given this level of damage, what's the likelihood of, so you show them spalling and you say, well, would you close a bridge or not? And my guess is we'll get some likelihood. So I don't know if it's a fragility curve, it might be just a decision tree, which is you get to, you have a 40% chance of spalling. And then if it spalls, you have a, I don't know, 60% chance of being closed. And you just follow the tree down. It's nothing fancy, but I don't know what else to do. If you have ideas, I'd love to hear that, because I find that the bridges that get closed are not necessarily the ones which my analysis would tell you have to close, but part of it is just psychology and public relations. So
that's exactly right. In two considered things, days we keep following the wind and shutting down bridges has a huge impact on your socio-economic responsibility.
Yeah.
Shutting bridges down just because of what's falling.
Right. So there was a study done for the state of Washington by the Department of Homeland Security, and they went to ask our Department of Transportation. They said, well, when do you start having damage in bridges? And the person says, well, when you get above a PGA of about 0.1 G, often we end up just closing the bridge. So the entire analysis is done and reports are written. And it's all based on if you're above 0.1 G and your bridge was built before 1980, the bridge is assumed to be shut down. So you're all looking around and smiling, but you realize that, gosh, if I take 0.1 G and apply that for a big earthquake, very quickly, based on an M9 earthquake off the Olympic Peninsula, they're looking at a bridge that's 200 miles away on the Columbia River. and they're saying it's closed. And it has huge impacts because the emergency managers get that, and they're not going to question that decision. The emergency managers see the map and they go, wow. So now the current plan for the state of Washington is you fly into Moses Lake, which is 220 miles from Seattle. And then you have helicopters. And they're going to bring all the water and the food to the poor stranded people in Seattle. And they're going to try to somehow keep everyone okay for months or who knows how long based on that. And your look is the same one that I had as well. In the history of earthquakes, I don't never seen a city be isolated to that extent by an earthquake. So anyway, you're absolutely right. It's not just about what's going to happen to the bridge, it's about what the authorities will do in response to that. So all we can do is do like a survey. We don't know what else to do, is to go talk to people and kind of get their opinion on what they're likely to do. We can educate a bit, but when I look at a bridge that has bars, columns are buckled, and I say, well, it's actually fine because you only need about 3 or 4 square inches of concrete to carry that load. That's not going to keep the bridge open anyway. So I'm sorry, I probably long answer to a short question.
So any other questions, especially to Jenny or Floriana?
So I think you mentioned there being 30 rupture realizations for some of the simulations around
The previous version, yes.
previous version. I think it would be really interesting to have a discussion going forward of how to constrain these rupture realizations.
Yeah. Yeah.
Because we're seeing, they got flashed up when we got tremendous variability,
Yeah.
depending on the specific rupture scenario. And I was talking to Norm about this, you want to make sure that you're sampling the tails of the distribution of the rupture model. So
That's hard to do, right?
It's a very difficult challenge.
Yeah.
You really have to do it, right? Otherwise, you get a bunch of heating motions that don't capture the breadth of potential motions at that side. So it seems to me one of the things that Pierre can do is to generate a discussion about the rupture model selection for engineering purposes, not precise modeling purposes, but engineering purposes.
No, absolutely. In fact, one of our conclusions from the first round is 30 is not enough, because that tail point is the 3% or something like that. And depends on what outcome. If you're looking at, for example, collapse of a bridge, it's a very, very rare event. You're also, you look at these 30 realizations and you realize 2 of them matter and 28 don't matter. And you go, oh gosh, how did I pick those 2? Did I get them just right?
You don't want to miss it.
Right? All of a sudden you change, yeah. Oh, good.
So, I think when you mentioned that we would want one of the next steps in the evaluation of the more conscious. So we're just wondering how we want to address it, just kind of time for
online people cannot hear these microphones, and we have to, I think also the people question that they thank you.
So Floriana asked what the plan for the validation is. So we have 4 different sites that we're doing validations for. We're looking at McDonald Island. We're looking at Honor Rancho. We're looking at a pipeline at Honor Rancho, and then another pipeline that goes through the East Bay of the Bay Area. So for all 4 of those, we're doing, it sort of depends. If they've experienced an earthquake in the past, then we're grabbing the shake map for that and running it through the actual facility and then comparing with the reported damage that happened there. The problem is there haven't been that many earthquakes that have caused significant damage at these facilities, right? So the other thing that we're doing for validations is sort of making fake earthquakes. So in some cases, for one of the, we created a pretend gas storage field and then just put a fault through the middle of it and said, okay, so now there's fault displacement across half of the wells and there's a huge amount of ground shaking. What kind of results are you getting in that scenario? And you would expect quite a bit of damage, right? So we're trying to, it's the same problem that Marc was just talking about. If you're doing all these simulations, but only 2 of them actually matter, what are you supposed to do? So in looking at the historical record in California, we don't have those to outliers that cause a lot of damage. So we're trying to push things as far as we can in sort of a fictional sense. We've also done, David and Tara did some laboratory testing of some of the components. So that's a way for us to test not the full risk model, but the pieces that are going into it, right? So those are the validations that are happening right now. Balboa Boulevard is the other validation that we're doing, where we do actually see some damage. Yeah, and that is the one that's going to be the most extensively documented, because for the other site locations, they're covered under NDAs. So we can tell you like either thumbs up, thumbs down, but we can't show you the details, unfortunately. But for Balboa Boulevard, we can. So those are the validations that are happening right now, and they've been performing pretty well. There were a couple models where they either caused too much damage or not enough, and when really pushing them to the limits. And so we're going back and taking a look at those right now to tweak them. I remember one of our early landslide models that we put into OpenSRA predicted landslides like everywhere in the state of California. And we were like, that's not right. And that was, you know, one that had was in publication for like 20 years and people had definitely used it. And then when we ran it for the entire state, it's like the state was covered in landslides. So we knew that one wasn't correct, and we've gone back and updated that. But yeah, it's interesting doing these validations because we're finding things like this. People don't usually run models over an entire state. It's usually for a specific site or. Yeah. Yeah. Oh, they can't hear online.
It doesn't, online, it doesn't work.
Yeah. Good point, Ian.
I will just say that it would be nice to kind of also have an interaction, see if, you know, we're gonna find the same model, the way we're going. I know these models are not really meant for that, but it would be so good to see them to just get them. Now, more detailed kind of approach.
Yeah.
Micro model, like, it's a really function based on model.
Mark,
Okay,
hold on a sec, Khalid. Mark's asking a question.
okay.
Go ahead.
I'm hard to speak loud enough to hear from the.
I don't think he can hear you.
We talked about NDA.
Yeah.
That's a good thing about gas and one of them.
Yeah.
I was asking what the minimum I need to develop to get some answer. Well, I know the pipeline is, I know the diameter.
Yeah, so for most of these, it's we haven't gotten it down to like age of the pipeline yet, though I feel like that should get pulled in at some point. But yeah, location, diameter, thickness of the pipeline. And a lot of these you can talk to the utilities and just have them give you a ballpark estimate. And that'll probably be pretty close to what's actually out there. There's less variability